Okay, well, our speaker today is Christopher Wulff, and he will speak about generalized asymptotic algebras and E-theory for non-separable C-star algebras. Christopher?
Sí, muchas gracias por la oportunidad de dar una plática aquí, pero voy a platicar en inglés porque mi español no es perfecto. So, so I will present my latest work about generalized asymptotic algebras and how to define E-theory correctly for a non-separable C-star algebra. And to get started, I should probably summarize what E-theory is. So E-theory is a type of bivariant K-theory, and I don't know if everyone has in the audience has worked with bivariant K-theory yet. So let me summarize the most important properties. So bivariant K-theory means we have abelian groups. In case of E-theory, they are denoted E of AB for all separable C-star algebras A and B. And they should have the following property, namely if A is the complex numbers, then we should get exactly the K-theory of the C-star algebra B. If B is the complex numbers, then we should get exactly the K-homology of A, although it is a bit unclear how to define K-theory the best. So this is like one possible, how to define K-homology the best. So this is one possible definition of K-homology. And another property which we want is that star homomorphisms from A to B actually give rise to E-theory classes E of AB. And then, like, perhaps the most important property is that there are these composition products. So in KK theory, they are called Kasparov products and denoted with a tensor product. But in fact, so these are maps from EAB, tensor EABC to EAC. And they actually turn these groups into the morphism sets of a category. So I will denote this composition product just like the composition in a category. And these composition products, they in fact generalize, or they extend the composition of star homomorphism. So if we plug in a star homomorphism, so the class of a star homomorphism from A to B here, and here the class of a star homomorphism from B to C, then we get exactly the class of the composition of those star homomorphisms. And yeah, or another way to express it would be that like we've got a functor from the category of C-star algebras into this new category whose objects are still C-star algebras, but whose morphism sets are exactly these E-theory groups. And then there are many more interesting properties, which I won't go into now. Let me just mention that one of them, which was also the motivation of this work, appears later on, namely the long exact sequences. But there are even a lot more properties which I will not discuss in this talk. And for those of you who haven't worked with bivariant K-theory yet, just think of it as a tool for computing K-theory. So a very, very useful tool. For example, if you take this composition product here and you let A be the complex numbers, then it specializes to this product from the K-theory of B, tensor this E-theory group to the K-theory of C. And now if we apply this, so if we plug in a star homomorph, the class of a star homomorphism from B to C here, then the map from K of B to K of C, which we get, is exactly the induced map of the star homomorphism. So this is a way to extend the functoriality, or in other words, we have functoriality under a bigger class of morphism than we had before, which is very nice. And now there's one drawback in almost all definitions of bivariant K-theory, and that is that usually, so almost all definitions require separability of the C-star algebras at some point or the other. So usually it's either at the definition or construction of the composition products of these products here, or if that works, then usually it appears later on when one tries to prove the long exact sequences. So for example, in Kasparov's original definition of KK theory, you really needed separability to write down the composition products. And the same was the case in the original definition of E theory by Kohn and Hickson. And but the model of E theory, which I will describe in the next few pages first, that's a model by Günther, Hickson, Trout that fixes at least the composition product. So that has, at least composition products for all C-star algebras, even non-separable ones. But there the problem lies in the proof of the long exact sequences. Yeah, and so my project, so for me, this was always very annoying because I come from coarse index theory. So I work with the C-star algebra of the row algebra and the C-star algebra and the stable Hickson corona, which is another C-star algebra, and they are essentially never separable. So for me, this was kind of annoying. And that's why I developed this new picture of E theory, which also works for non-separable C-star algebras. And to explain how I did it, I really have to dive deep into the definition of E theory. So this talk might be a bit technical. I'm sorry about that. So E theory is modeled is modeled on so-called asymptotic morphisms. So what is an asymptotic morphism? Let's look at the lower part of the slide first. So an asymptotic morphism is essentially a family of maps from A to B, where we've got like one parameter T, which is in the which is a real number greater or equal than 1. And like for each A, these phi T should be continuous in this parameter T. And then these phi T, they should behave asymptotically as a star homomorphism. And this can be expressed as follows. So if like phi T itself would be a star homomorphism, then it would mean that these three terms would have to be 0. So like here, linearity, multiplicativity, and the star property. But now for these asymptotic morphisms, we only require them to converge to 0 in the limit T goes to infinity. And another way, maybe a more elegant way to express it, is to define this asymptotic algebra of B. So this is the C-star algebra of all bounded continuous functions from this ray in which T lives to be modulo the C0 functions. And then an asymptotic morphism from A to B is nothing else but a star homomorphism from A into this asymptotic algebra of B. And it's rather easy to see that these phi are represented exactly by families of this lower type. So that's what an asymptotic morphism is. Yeah, and this formulation was the one by Günther, Hickson, and Trout, which is like my standard reference for the first half of the talk. I will always refer to them. And before I go on with the construction of E theory, I should maybe give you an example of such an asymptotic morphism. And this is a very nice example which comes from index theory. We will see a different type of example later on. Namely, assume we've got a compact manifold M and then a Dirac bundle over it. So a bundle with a Hermitian product and a Clifford action and a connection, which are all compatible. And associated to it, there's the Dirac operator, which is a self-adjoint unbounded operator. Then we can define an asymptotic morphism from C0 of R tensor C of M, the continuous functions of M, into the asymptotic algebra of the compact operators on the L2 space of this bundle. And this is defined as follows. So first, we take function f in C0 of R. So this is the f. And we use it to do functional calculus on the Dirac operator D. And then we take a function g, a continuous function on M, and we multiply it with it. And that's an, a compact operator on the L2 space. But now this definition without the T wouldn't give a star homomorphism, right? Because like f of d and g, they don't commute in general, but this commutativity would be necessary to obtain a star homomorphism. But what's nice is that these two commute in the limit if t goes to infinity. So in the limit t goes to infinity, we have this property, so it's actually an asymptotic morphism. And an asymptotic morphism like this is very useful for doing index theory. So for example, there's Dirac operators, they always have k-homology classes. And in this picture, the k-homology is simply the E theory of C of M, C. And so I haven't told you yet what how E theory is defined, but I just said it's modeled on asymptotic morphisms. So essentially, this asymptotic morphism now defines a class in this E theory group in this K homology, and that's the fundamental class of the operator D. And maybe you have seen this class also defined differently. So it's the usual class, which has the nice property that if we consider the pairing between K theory and K homology, which can also be considered as this E theory product here from this E theory group, which is K theory, to this tensor, this E theory group, which is K homology, to this E theory group, which is isomorphic to the integers, then this pairing has the property that it maps the class of a vector bundle and this fundamental class here to the index of the twisted Dirac operator. So this is very nice. So these classes are very useful. Okay, so this example will, I will come back to this example later on. And so before I go on and describe the construction of E theory, I should probably mention this functoriality, which I mentioned on the first slide. So the first part is again the definition of asymptotic morphism from the same slide from the slide before. It's exactly the same. Assume we've got a so how can we describe the functoriality of K theory under asymptotic morphism? So on the first slide, I said K theory is functorial under E theory elements, and here it's a bit more general. It's functorial under asymptotic morphisms. How does this work? So assume you have a K theory class, which is represented by a projection in a matrix algebra over A. And then we can apply this asymptotic morphism, so this phi t, to the projection. And what we then get is not always a projection, but if t is large enough, then this is close to a projection. And so we can squeeze it a bit to get a true projection. And then the image under this functoriality, under this asymptotic morphism, would then be exactly the class of this projection, K of B. Or a more formal way to express it is, now if we start with K of A, then we can apply this phi. We can use the functoriality under this phi, which was now in this description of asymptotic morphism. So we end up in the K theory of the asymptotic algebra of B. And now, since this C star algebra here, the C0 functions of B, since this is a contractible C star algebra, the long exact sequence in K theory associated to this quotient actually gives an isomorphism between the K theory of the asymptotic algebra and the K theory of the bounded continuous functions with values in B. And now when we're here, we can evaluate it at 1 or at any other time t, and we get an element of K of B. And that's exactly the functoriality of K theory under asymptotic morphisms. But when I say functoriality, then so under functoriality, one normally understands functoriality under morphisms of a category. But I haven't made asymptotic morphisms in a category yet. So the question is now, can one make a category out of asymptotic morphisms? And that's actually a question which is the first step towards the definition of E-theory. And so the problem here is, so I've got a paper here. I hope everyone can read it when I write here. So assume you've got two asymptotic morphisms, say phi or phi t. So we've got like one family of maps phi t from A to B, which defines one asymptotic morphism. So I hope everyone can read it. And if I have a second asymptotic morphism given by a family psi t from B to C, then the naive way to compose them would be simply to compose them. So we take psi t composed with phi t, and that gives us a family of maps from A to C. But now the problem with this construction is that if we compose them naively like this, then we will usually not get an asymptotic morphism anymore. Because like the asymptotic properties which we have to fulfill, so psi t would fulfill them if we put something fixed in here, but now we don't put something fixed in here, but now we put something else in here which also depends on t. And this can be solved if we reparameterize this t here. So we can take a function s of t. So s is now a continuous function which converges sufficiently fast towards infinity. And so if s converges sufficiently fast to infinity, then this composition here would again be an asymptotic morphism. And that's what we can define as the composition of asymptotic morphisms. And that's actually the way in which Kohn and Hickson defined their composition product on their E-theory groups in their original picture of E-theory. So, but there is a slight problem with it, namely, we can find such a reparameterization S of t if A is separable, but not necessarily if A is non-separable. So that's the point where their original definition of E-theory actually needs separability. And now there's a more modern, more elegant way to construct a composition. And that's again in this paper by Günther, Hicks, and Trout. And what they did is, so they took here, now they worked in this formulation of asymptotic morphisms. So they took one asymptotic morphism from A into A of B, and another one from B into A of C. And now, since this A here is a functor, we can compose phi with A of psi, and then we end up in the iterated asymptotic algebra of C. And this, of course, works for all non-separable C-star algebra. Here we didn't need any reparameterization, but of course, if we want to make a category out of it, this now means that we have to also consider these higher iterations of the asymptotic algebras. And there's another thing which we need to, in order to make a category out of it, namely we have to divide out a suitable notion of homotopy out of these classes of asymptotic morphisms. And this is the notion of n-homotopy. So now we are considering more general star homomorphisms from A into the n-fold iterated asymptotic algebra of B. And two such star homomorphisms would be homotopic in the usual sense if we find a star homomorphism phi from A into the continuous functions from this interval 0, 1 to A to the n of B. That's where we are working in now, which evaluates to phi 0 and phi 1 at times 0 and 1. But that's not the notion of homotopy which we are using here, but instead we're using what we do differently here is we exchange this asymptotic algebra and this continuous function. So these are exchanged with each other. And this leads to the notion of n-homotopy. So in this definition, you now see the a to the n is now outside of this C0, 1. And so if phi0 and phi1 are homotopic in the usual sense, then they are also n-homotopic, but not the other way around. So here we actually get more equivalent elements, more star homomorphisms which are n-homotopic to each other than star homomorphisms which are homotopic to each other in the usual sense. But of course, if n is equal to 0, then this is the identity, then we get exactly the usual notion of homotopy. And now, if we divide this notion of homotopy out, then we get some homotopy class, so some sets of homotopy classes. Let me denote them by A, B, and then N. So this is the set of homotopy classes of set of n homotopy classes of star homomorphisms from A to the NB. And okay, now you probably wonder which n do we take? And well, the n we take is not a single n, but actually we take a direct limit over all n, where n goes to infinity. And this way we can define the asymptotic category. And now the point is, there are canonical maps from these n homotopy, from the set of n homotopy classes to the set of n+1 homotopy classes. And they are induced by star homomorphisms from A n B to A n+1 of B. So recall that these here are essentially, so these asymptotic algebras are essentially represented by functions in n variables, and these here are represented by functions in n+1 variables. And the way to get a function in n+1 variable out of a function of n variable is to make this new function independent of the additional variable. So and be the old function on the rest of the variables. And now the funny thing is, up to n+1 homotopy, it does not matter which of these n+1 variables is the new one and which are the old one. And that's why, so these maps down here, they are canonical up to n+1 homotopy, and that's why we get canonical maps between the n+1 homotopy classes. And with using them, we can now define these direct limits. I denote them with these double brackets, or sometimes with the subscript A, also to indicate that this is the construction using asymptotic algebras, in contrast to what I do later on. And yeah, these are the morphism sets of the asymptotic category. And now the products, they can be defined exactly by the idea which I had before. So if we have a star homomorphism from A into A to the MB, like this phi, then we can compose it with a star homomorphism from psi to A to the, say, N C, if we apply this functor A to the M, and we end up in this group here. And this composition, it's compatible with these n homotopy classes, and it also passes to the direct limit. And that way, one can see that these sets here, they always have a composition product, which turns them into a category. So these sets, they are the morphism sets of a category, and that's always the case. We didn't need any separability here. But if we assume separability, then it becomes a bit easier. Namely, then one can show with a similar reparameterization trick to what I have mentioned before, similar to this reparameterization trick, one can show that the canonical map from the one homotopy classes here into this direct limit is in fact a bijection if A is separable. And yeah, and this now gives us a category, and from this category, it's rather straightforward. Maybe I should move a bit to the side so that you can see my slide. From these morphism sets, one can directly define the E-theory groups. And what one does here, so the E-theory of AB is essentially the morphism sets from A to B in this category, just that we added some decoration here. So there are different types of decorations which one can add. There are different versions. But like, for example, one can suspend it by tensoring with C0 of 0, 1 and with the compact operators. And if we do it on both sides, this has the effect of making abelian groups out of these morphism sets. And that's how you define E-theory. And because we had the morphism sets of a category before, these groups here, of course, always have a composition product. And yeah, so that's the definition of E-theory by Günther, Hicks, and Trout. But I shall mention for my talk, so you actually don't have to remember this decoration here. So my talk is more a talk about these morphism sets, and E-theory is then just these morphism sets plus a bit of decoration. So you don't need to recall all the details in here. Okay. And now, so this is very nice. We've got a picture of E-theory, which has all composition products. So what's the drawback? And the drawback is, as I mentioned at the beginning, there's another nice property which one would like to have, but which we can only show in the separable case. And that's the long exact sequences. So assume we've got separable C-star algebras AD and then an ideal I in A. Then there are two long exact sequences. So in the first one, we fix in the first component always the C-star algebra D. And in the other component, we have the maps induced simply by the maps from I to A and then into the quotient here. And we can extend the sequence to the left where the suspension appears. And dual to it, there's also a sequence where the first entry varies and the second entry is this fixed C-star algebra D. So here this E, so here it's covariantly functorial in the second entry, but contravariant functorial in the first entry. So here we go exactly in the other way around. And now, where does separability enter? It actually enters in the description of the boundary maps here. These here. So these boundary maps, they are actually given by a composition product with another E-theory element. And this E-theory element can be directly written down. So it's essentially given by an asymptotic morphism. And to define it, so it's defined in the following way. Namely, we first choose a quasi-central approximate unit of the ideal I in A. So what is a quasi-central approximate unit? Well, in this case, it is a sequence of elements in I. So the UN are in I. They are all positive elements and they are all less or equal than 1. So the ideal doesn't have to contain a 1, but if we embed it into a unital C-star algebra, then these UN should all be less or equal than 1. And so it's supposed to be an approximate unit. So if we multiply UN with J and let n go to infinity, then we should get exactly J. Also in the other way around, but that's implied by the third property, namely that in addition to being an approximate unit of the ideal I, it should be quasi-central in A, which means that these UN, they should commute with all A in the limit n goes to infinity. So that's a quasi-central approximate unit. And what can we do with it? Well, we can, first of all, extend it to a continuous map on the ray from 1 infinity into I. And now this map U can be defined, can be used to write down an asymptotic morphism. And this asymptotic morphism now goes from A modulo I tensor C0 of 0, 1.
Can you
okay,
see the chat? Yes.
Yes, I just saw it. Dev asked why quasi-central approximate units exist. So that's the point, namely here. So sequential quasi-approximate units exist because the C-star algebras are separable. I don't know if that was your question, but in general, yeah, so there are direct constructions of quasi-central approximate units. So for example, one can take all elements U between 0 and 1 and order them with a partial order, then you've got a directed set. And if A and I are separable, then you can find so you've got this net, and if A and I are separable, then you find a cofinal subsequence in there, and this subsequence is the quasi-central approximate unit. Okay, apparently that answered his question. And yeah, so right, and now we've got this continuous map here, and we construct this asymptotic morphism out of it, like from the suspended quotient A modulo I tensor C0 of 0, 1 into the asymptotic algebra of I. And how does this work? Well, we take the class represented by an element in A, so the class of it in the quotient, tensor a function here, and what we do is we multiply A with and now we use the function here to do functional calculus on this element ut, which is of course between 0 and 1. So this is perfectly fine here. And again, one can show that in the limit t goes to infinity, this is actually a star homomorphism. So we get an asymptotic morphism in this way. Okay, so you don't really need to calculate all the details in here. So let me just say this is an asymptotic morphism. And then again, if we add some decorations like compact operators and so on, then what we actually get is an E3 element in E of A modulo I tensor C0 of 0, 1, comma I, and the composition product with this element now gives us exactly these two maps here. These boundary maps and the long exact sequences. Okay, and now the important thing is that the existence of these elements here, they are not only necessary to describe the boundary maps, but they actually play a big role in the proof that these sequences up here are exact. So if we don't have these elements, then our proof of exactness breaks down, or our proof, so the proof by Günther-Hexentraut. So that's why these elements are really essential for the theory. Okay, and now what's different in if we have non-separable C-star algebras? Well, then the problem is that in general, we don't have sequential approximate units, but our approximate units are now, so they are not indexed by the natural numbers, but now they are indexed by a directed set M. So I use this Fraktur M to denote directed sets. And of course, if we have such a net, then we cannot extend it to the ray. But what we can do instead is we can extend it to the geometric realization of the full simplicial complex with vertex set, this directed set M, simply by linear interpolation. So we've got this possibly infinite dimensional simplex whose vertices are the elements of the directed set M. We know the UMs at every vertex, and now we do a linear interpolation between them. And then using exactly the same formula as before, this formula here, we can now define a star homomorphism from A modulo I tensor C0 of 0, 1 here. Doesn't mark where I want it to mark. but now not in the asymptotic algebra, but into something which I call the simpletonic algebra. So now this T is an element in this infinite dimensional simplex here. And what we get here is the bounded continuous functions on this infinite dimensional simplex with values in the ideal I modulo the C0 functions. And this quotient is what I call the simpletonic algebra, because it's modeled after simplices and it's similar to the asymptotic algebra. And I should perhaps just say what I mean by C0 functions here. So what's that? This, if M is, so if M is now infinite, then these simplices, they are not locally compact spaces. So it's not really a good idea to define C0 functions as functions which become arbitrarily small outside of compact subsets. But instead, we want them to become arbitrarily small into the direction on the simplex, which is given by the directed set M. And the way to do it is we look at the tail. I denote the tail like this. So this normal M is an element in this directed set Fraktur M. And then I consider the tail. So all elements in the directed set which are at least as big as this M. And now these C0 functions should be functions such that for each epsilon here, there exists such a tail such that if we restrict F to the geometric realization of the full simplex of this tail, then this should be less or equal than epsilon. So that's our notion of converging to 0 as we go to infinity. And these notions like the simpletonic algebras and the asymptotic algebras, they can be unified if one considers bounded continuous functions modulo C0 functions, where the notion of C0 function is given by a filter on the space X. So that's like what they have in common. And then I would talk about generalized asymptotic algebras. But here, let's just look at this special case. So essentially, a simpletonic morphism or the simpletonic algebra is now bounded continuous functions on the simplex modulo the C0 function, where the C0 notion is given by the order by the order on the directed set M. Okay, and now the whole idea of my project was, if we want to have a model of E theory where we have long exact sequences, even for non-separable C-star algebras, then we should define E theory modeled on these new simpletonic algebras instead of the asymptotic algebras, because then we have a chance that these star homomorphisms here actually give rise to E theory classes, which we can then use to prove the long exact sequences. And so that's what I did. And now here so many of the following definitions are reminiscent of what I had shown before. So again, we need to divide out a notion of homotopy. So here we now consider star homomorphisms from A into the simpletonic algebra of B. So by the way, this is a Fraktur S. So like simpletonic. And now we divide out a notion of M homotopy, which is again defined in exactly the same way as we had before. So with these two exchanges, but now with the simpletonic algebra instead of the asymptotic algebra. So it's essentially exactly the same definition. And and now we want to make a category out of these elements. But before I do this, so before I go on, I should probably tell you what these sets here, these M homotopy classes, have to do with the homotopy classes of asymptotic morphisms, which we have seen before. And now this is like the most important example of this theory. So how the simpletonic and the asymptotic classes are related. Namely, if the directed set M is simply the natural numbers, and for convenience, I let the natural numbers start at 1 in this talk, then we can write down two continuous maps. Namely, first, we can embed the ray from 1 into infinity into the simplex with vertex set the natural numbers. And that's simply done by walking like from the vertex indexed by 1 to the vertex indexed by 2, and then to the vertex indexed by 3, and so on. And that's that exactly embeds the array into the simplex. And we can also go the other way around from the simplex to this array with this formula. So by taking an abstract linear combination of these lambda n times the vertex n, map it to this linear combination in R. And now both of them are continuous, and this is an inclusion, and this tau is actually a retraction onto the image of the inclusion. So one of the compositions is the identity, the other is not. And both of those functions, iota and tau, both of them are compatible with these filters defining the C0 function. So if we pull back a function, a C0 function on the simplex, then we get a C0 function on this array and the other way around. So iota and tau, they actually define star homomorphisms then on the quotients between the asymptotic algebras and the symptotic algebras with respect to this directed set, the natural numbers. And now if we take the composition with them, then we get two maps from the one homotopy class of asymptotic morphisms to the to this class of homotopy class of symptotic morphisms, and the other way around. And they are actually bijections. So that's like the relation between the asymptotic side and the symptotic side. That we, in this case, for this directed set, we get these bijections here. And okay, and now we want to make a category out of these sets. So how do we do that? And here we use a similar trick. So we don't just take one m, but we want to take the direct limit over all m when m becomes bigger. So how does this work? Well, this works in the following way. Namely, if we have a cofinal map from one directed set m to n, so this cofinal map essentially means that this directed set m is bigger than this directed set n, then we can extend it to the whole simplices and then pull back functions under this induced continuous map here. And that gives us a star homomorphism from the n symptotic algebra to the m symptotic algebra. And now the funny thing here again is that the m homotopy class of this star homomorphism does actually not depend on the choice of the cofinal map A alpha. So that's similar to what I said before. Like if we want to make this function out of in n+1 variables out of the functions in n variables, then we define the new function just as the old one, but it's independent of the new variable. But like which variable is the new one doesn't matter. We can take any of them. And that's similar here. So which cofinal map we actually take is completely irrelevant for the M homotopy class of this star homomorphism. And therefore, we get canonical maps from this morphism set here with respect to n to this morphism set m whenever a cofinal map exists. But which cofinal map we choose is irrelevant. And now, so if we declare m to be bigger than n, if such a cofinal map exists, then we can take the direct limit as m becomes bigger and bigger and define this direct limit here. Or can we? There is one slight set theoretic thing which we have to consider, namely all directed set together, they don't form a directed set again, but they only form a directed class. So this direct limit here is actually not a small limit of sets, but a limit over a big class of things. And so we have to argue why this limit actually exists. And this limit exists for a very a nice reason, namely because the system becomes constant for m large enough. So in particular, the direct limit is isomorphic to one of those symptotic morphism sets if this m is a large enough directed set. And I can actually write down a very specific directed set from which on this becomes constant the system. And this directed set M has the nice property that it only depends on a dense subset of the C star algebra A. And in particular, if A is separable, then we can take a countable dense subset of A to construct this M. And the resulting M will again be separable. So for separable C star algebras A, we can always find such an isomorphism for a separable M. And now when we're at a separable M, it's it's possible to simplify it even further, to simplify it namely to the natural numbers. And then if we know, so we've got this isomorphism for the natural numbers if A is separable. And then when we're at the natural numbers, we can apply the example, which I had on the slide before, which said that for the natural numbers, we simply get the asymptotic morphism set. So the result is that if we have a separable C star algebra A, then these symptotic morphism sets are exactly the same as the asymptotic morphism sets. So that's of course very nice because we want our new theory to be equal to the old one in the case of separable A. Okay, and now that we have defined these morphism sets as this direct limit, one can define the composition product. And this is actually the ugly part of the theory. So essentially, the composition products are now defined more or less by the same formula as before. So we take a symptotic morphism from phi from A into SMB. And we take a psi from B to SNC. And we apply this functor SM on psi, and then we can compose it. So that's exactly what we did before with the asymptotic algebras. And then the resulting star, so then the composition will end up in this iterated symptotic algebra. But now the point is, in this case, I didn't define the symptotic morphism sets by iterating the symptotic algebras, but instead by making the directed set larger and larger. So we have to go from here into the non-iterated symptotic algebra with respect to another directed set of B. I think there should be a C here. And essentially an element here is represented by a function on this product. So to get an element here, we just have to pull back this function by such a map here, a continuous map from this big simplex into the product of these simplices. Now, and the ugly thing, why I also won't write down the formula, is that the directed set which I need here, I don't explain this now, this has to be huge. It's a monster, it's a real monster. You don't really want to work with it. But I had to choose a very big set, otherwise the construction didn't work. And this set here, this map is also not the product of two simplicial maps, which also makes this map very ugly. So that's why it's really ugly to work with this, to explicitly write down the composition product. But let me tell you, it works. It's compatible with all the homotopy classes, and it passes to the direct limit. So we really get the morphism sets of a category. And what I was also able to show was that we actually have canonical maps from the asymptotic morphism sets into the symptotic morphism sets. And together they constitute a functor from the asymptotic into the symptotic category. And again, for a separable A, these maps are bijections. So now we really got the symptotic category, which is equal to the asymptotic category for separable C-star algebras. But for non-separable ones, it can behave differently. Okay, and now time's running short. So now if I want to have E theory of non-separable C-star algebras, then I do essentially the same thing as before. I take now the symptotic morphism sets. So this is denoted by this index, and I add some decorations. Instead of just tensoring with the compact operators on a separable Hilbert space, I now also want to consider the compact operators on non-separable Hilbert spaces. So this H here can be non-separable, and of course, which Hilbert space do we take? Well, we take all and then take the direct limit over arbitrary large Hilbert spaces. So, but essentially E theory is again, now the symptotic morphism sets plus some additional decoration. And yeah, I know I'm kind of already going over time, but let me just say the last few things. So there are, now that I've defined this E theory, I was able to show that it has like all the nice properties I'm interested in. So if I concretely work with E theory to do index theory, and I need the products, the long exact sequences, and I was also able to show a lot of other properties. And one property which one would of course like to have from a theoretical point of view, although it's like not so relevant for me, would be that it satisfies the universal characterization of E theory. So E theory can be described by a universal characterization. And yeah, it would be interesting to check this. I haven't done it because it's not really relevant for me. So that's like one open question. And now the other open question, that's more, the second one is more the direction in which I want to proceed with this research is, now that we have this new model of E theory, modeled after symptotic morphisms, now, are there geometric situations which give rise to canonical symptotic morphisms, which then give canonical classes in E theory, with which we work with? Because like with the symptotic morphisms, we got a lot more flexibility than with the asymptotic morphisms, which we had before. And can we, so the theory is more complicated, but the question is like, can we make use of the fact that it's also more complicated in the sense that now we have more nice cycles? And to illustrate where I would try to look for these new cycles, I want to recall this example which I had before, namely this asymptotic morphism here constructed from a Dirac operator on a compact manifold. And for compact manifolds, this works nicely, but there are two situations where I think where in my opinion, this new flexibility with symptotic morphisms enters quite nicely, quite naturally. Namely, first of all, one can consider what happens if we want to consider index theory on infinite dimensional manifolds. So there's a lot of unclear in index theory on infinite dimensional manifolds, but the idea behind it, which I had was now for an infinite dimensional manifold D, it might be a good idea to not rescale the operator D by one constant factor in all directions, but we might want to use different factors in different directions to rescale the operator D and get such a formula. And indeed, so there was one construction, which I'm thankful to Rufus Willett for pointing this out to me, namely Higgs and Kasparov-Trout proved a version of Bott periodicity for infinite dimensional Euclidean spaces. So M is now an infinite dimensional Euclidean vector space. And deep in their paper, so they were working with asymptotic algebras, but deep in their paper, there was a construction which is actually more natural and works in more generality if we reformulate it as a symptotic morphism. And that works. And in that case, the directed set M would then be like the directed set of all finite dimensional subspaces of M. So that's like one situation where I identified symptotic morphism, which appears really natural. And that's why I really believe that this new model of E theory might be good to do index theory on infinite dimensional manifolds. And another example, which I found in an old paper of mine, which I wrote several years ago, which I had almost forgotten, was there I was working on coarse index theory on complete Riemannian manifolds. And there at some point I constructed an E theory element. Well, actually not really an E theory element, but an element in an inverse limit of E theory groups. But now I realized that if I use the language of asymptotic morphisms, then I would really get a true E theory element. And what's the idea here? So the idea is essentially for a complete Riemannian manifold, so a non-compact manifold, it might not be a good idea to rescale with the same parameter all over the manifold, but like to use a different parameter at different places of the manifold. So we want to rescale with a function on M instead of one parameter T. And well, the correct way to do it is to use a conformal change of metric and then look at the Dirac operator of this conformally changed metric. So that's essentially the real rescaled operator. And now here, the lambda is a function from M to 1 infinity, and the corresponding directed set, which one would have to use is, well, the directed set of all smooth functions from M into this ray. And in that way, we would get a asymptotic morphism, which really gives us a canonical E theory element. I haven't quite worked out everything here yet, but I'm confident that it works. Okay, and I hope that these two examples convince you that this new model of E theory can be very useful for this type of index theory. And I think I'm already far over time, so I'll stop here. Thank you very much.
Okay, thank you, Christopher. Very nice talk. Let's see if there are any questions.
I have a question.
Yes, Dan?
But it's not specific to your talk. It's more about E theory in general. So most proofs I've seen for excision in E theory, they use the fact that the category of either separable or in your case, non-separable C-star algebras have these quasi-central approximate units, which seems kind of weird because this should be an intrinsic property of the category itself, and it should not rely on something as weird as the existence of approximate units. But the proofs, they all seem to very crucially rely on the existence of approximate units. Do you know if there is a way to prove such statements without using approximate units?
No, I mean, so essentially, when you talk about excision, so excision is actually the part which is needed to prove these long exact sequences here.
Yeah.
And so actually one needs these. So here I said before that one needs these delta here, these asymptotic morphisms to not only write down these boundary maps, but also to prove that the sequences are exact. And that was partially a lie because one actually just needs these sequences in the special case where we have like a suspension, right? So where these delta are then exactly the excision homomorphisms, right?
Mm-hmm.
I think it was something like this. It's definitely related to this point. So I mean, the point is like one can always write down a long exact sequence, which looks a bit different than these here. But if we want to come back to these long exact sequences, then we exactly need this excision. And this proving the excision, it actually just makes use of these asymptotic morphisms in exactly this form. But just for a special case, I think, if I remember it correctly.
Mm-hmm.
And I mean, I don't know how you want to do without it, because in the end, I mean, what's E theory about? What's so special about E theory? Well, what's special about it is that it's modeled after asymptotic morphism. So at some point, like, yeah, you probably need this asymptotic morphism to need some asymptotic morphisms to get excision. I mean, to contrast it from non-E theory in a way.
Yeah, well, my
If you
motivation
understand
comes
what
from extending things like E theory to things more general than C-star algebras.
okay.
That's where my insistence on approximate units comes from.
Okay. Yeah.
And well, you usually have you have local cyclic homology, which has all these properties as well, but it is defined on something larger than C-star algebras. So it would be nice to have an approximation of bivariant K theory, which maps into things like local cyclic homology. And the candidate approximation is E theory, but all the proofs I've seen, they use exactly this delta that you've written down.
Yeah. Yeah, but I mean, that's kind of the point that like, I only got the long exact sequences here for non-separable C-star algebra because I was then using more general algebras than the asymptotic algebras. So I used more general asymptotic algebras, the symptotic algebras. And so I mean, if you wonder, well, why can I do this one proof with symptotic algebras and not with asymptotic algebras? Then, well, that's exactly because I used this type of construction here.
Okay.
I mean, or to express it this way, if there was like a proof of excision, which would work without using this element here, without this asymptotic morphism, then it should also it should also work for non-separable C-star algebras, and that would kind of mean that my new picture of E theory would somehow agree with the old one defined with asymptotic algebras. So that's what I expect. Right. And but then the question is, okay, what happens to all this information which is in these symptotic algebras? Why should that already be in the asymptotic algebras? And so you understand what I mean? So I expect this, I don't expect this information to be already contained in the asymptotic algebras. So right. in this case, so to me, it feels like as if such asymptotic morphisms or more general symptotic morphisms must be necessary to get some kind of excision. But who knows? And yeah, in the case of more general algebras than C-star algebras, well, maybe you also have to go this way and like define a more general version of asymptotic algebras then.
Well, that exists in, let's say, Ralph's book. But I mean, I could give you a reference later.
So I assume you're working with something like Banach algebras, or what are you concretely?
Well, for instance, I'm also working over the periodic integers. So things like C-star algebras don't make sense. But yeah, I mean, even over the complex numbers, I would like to see a version of E theory for just Banach algebras or inductive limits of Banach algebras.
Yeah. So without knowing too much about what has been done in that field, I assume you just need the right notion of asymptotic morphism in this sense.
Yeah.
So a right generalized version of it.
It's just that the part where it breaks down is that these proofs use approximate units. So there exists a version of approximate of asymptotic morphisms as well.
Okay, I understand. Yeah.
Yeah, it's a bit technical, so I could tell you about it later.
Yeah.
Okay. Any other question?
Hello, Christopher.
Hello.
Hi, very nice talk, very inspiring. Thank you.
Thank you.
I'm wondering, what about KK theory? So I suppose you probably have already considered that.
Well, I must say that, like, from the history of my own publications, I kind of grew up with E theory and not KK theory. So for me, it was like more straightforward to work with E theory. And well, I mean, I don't know. It's so okay, about KK theory. So what you can do, I think there is a picture of KK theory, which is essentially the same as the picture of E theory, just that you ask the star homomorphisms to be additionally. So I think there's the picture. So E theory, where's the definition? Yeah. So I defined E theory like as the asymptotic, or they defined E theory as the asymptotic homotopy classes, these morphism classes in the asymptotic category between those two C star algebras. And I think if you want to get KK theory, then you can define it in a way where you now take asymptotic morphisms from here to here, but which have an additional property, namely that they have a completely positive lift to the bounded continuous functions or something like this. I'm not very familiar with it, but
yeah, I think you're right. Thomson's picture, yeah.
So there was a picture, right? So not only from A to AB, but additionally a lift into this here, completely positive. I think yeah, that's what I heard. I haven't worked with it, and of course you could then take my definition of E theory for non-separable C star algebras and yeah, and then ask for this additional property. Then you might get KK theory for non-separable C star algebras. But that, of course, relies on this concrete picture of KK theory, which is very similar to the E theory definition. Like if you want to start with the KK theory, the original KK theory by Kasparov, then I mean, that's a completely different picture where my idea just doesn't have anything to do with it. So I don't know how I would work there.
Yeah, I guess so even with Thomson's picture, so so this notion of, even with Thomson's picture, the picture of KK theory just mentioned of liftable to CP maps. I was just thinking, with what you're doing now with this abstract framework, I guess lifting still makes sense. Lifting from your synchrotonic, so these synchrotonic morphisms, you can still talk about like them being liftable from A into some into your CB.
Right.
Yeah.
Right. I mean, the definition, where was the definition? It was somewhere here. So I mean, it's exactly again defined as CB modulo C0 here, just that, yeah, the CB functions are now in a simplex. So we would still have like, yeah, star homomorphisms like this, but now with a lift into the CB up here.
I see. Yeah, that makes a lot of sense.
So I mean, that's what one could try. I of course haven't worked it out because I was too fixated on E theory.
Yeah, it's very elegant. Thank you.
Okay, another question. Not, I will stop the recording. If I can.